Now is the turn of Francesco Piro. He's a master student at Politecnico di Milano in Italy. He's researching on quantum programming and quantum logic and his relationship with or the impact on artificial intelligence. So he is going to present a work with Mernus Ascarpour and Elisabetta Di Nitto. So Francesco, are you ready?
Yes. Good evening, everybody.
Okay.
Now I'll share my screen. Okay. Can you see the first slide of the presentation?
Yep.
Okay. So I can start. Okay. So first of all, good afternoon, everybody, or good evening, depending where you're attending this presentation. I'm going to present a work that I made together with Mernus Ascarpour and Elisabetta Di Nitto. Elisabetta is a full-time professor at Politecnico di Milano, while Mernus is now a postdoc at the McMaster University. My name is Francesco Piro. I'm still a master level student at Politecnico, and I define myself as a quantum computing enthusiast. In particular, I started studying this new area almost 1 year ago, thanks to a project that I started with Elisabetta and Mernus. And then we decided to find a venue to present our work that would fit the topics that we were discussing, in particular from a software engineering and technology point of view. So in this work, we're going to see a more practical example, in particular, a real implementation, or better, a generalization of a solver for a problem that focuses on some of the areas that now I am studying during my master level. Okay, so first of all, with a brief introduction, I wanted to focus even more on the fact that we're going to talk about logic, computational theory, and artificial intelligence. And in order to do it, we decided to consider the satisfiability problem, which is one of the most important ones, in particular for computational theory, since it is the first problem proven to be NP-complete. And this conclusion led to further very important studies that are now going forward the problem of the equivalence of the P and the NP classes. We studied the quantum computing literature and found that actually a solver for the SAT problem already exists, in particular for a slightly easier version called the Exactly-1 formulation. This solver is by Nannicini. It is based on Groover's search algorithm, and we will see an implementation based on the Qiskit library provided by IBM. Okay, so first of all, it is very important to understand the definition. On the top, we have the general formulation of the SAT problem, but as I've just said, we will consider its Exactly-1 formulation. So it is important now to read all together the definition. Given a KSAT problem, we want to determine a satisfying assignment containing 1 to literal per clause. So we will see in the generalization of our work how to look for a solution in a quantum way means. And also in the conclusions that we provided, we can understand how to find it once we provide the histogram that our solver is returning. From this slide, it is very important to understand the numbers on the bottom, in particular, because our generalization is based on top of them. N is the number of variables on which the problem is defined, M is the number of clauses, and K is the maximal length of the clauses. Okay, so as I have said, the algorithm that we're going to study is based on Groover's algorithm, quantum algorithm that exploits the amplitude amplification quantum principle. And in particular, it perfectly fits the kind of search that we are doing in our case. In fact, we're looking for exactly 1 true variable for each of the clauses that define the SAT problem. And so we can exploit its basic idea of bringing all the basic state to the uniform superposition and iteratively increase the coefficients of the correct solutions by doing the two steps on which Groover iterates. So the first one flips the sign of the vector for which UF gives output 1. UF is the matrix that encodes in the circuit, in the quantum circuit, our problem as a function f, and then we invert all the coefficient of the quantum state around the average coefficient. Okay, Nannicini's work is able to solve at most an exactly one 3 SAT, so k equal to 3 with n equal to 3 and m equal to 3. It is structured in the same steps that we described for the definition of Groover. They are called the initialization, the problem encoding, and the inversion about the average step. Our generalization will focus on studying more complex instances of the exactly-1 problem, in particular generalizing in terms of m, n, and k. Okay. So now we can start talking about our generalization. In particular, these are the main 3 steps of it. The first one wants to allow for arbitrary numbers of variables and clauses, so n and m. The second, to allow for an arbitrary maximal length of the clauses. And the third is an additional study that we gave to this work related to the best number of iteration of a Groover algorithm. Since, as we know, it is one of the most important issues of this algorithm, as also this famous quotation of Christian Fuchs says, because it is not possible a priori to, or well, it is not impossible, but it is very difficult to know a priori which is the best number of times to iterate the algorithm in order to find the solution. In this case, we have a metaphor between a quantum oven and cooking a souffle inside of it, and this quotation says that if we open the oven too early, the probability will drop to 0, as well as if we overcook the souffle. So we are going to see how this is reflected inside our solutions at the end of the presentation, once we understand how the generalization actually works. During the generalization, we mainly found 3 issues. The first one is to design a circuit with precisely counted qubits. The second, to realize a kind of gates that is not present in the basic operation of the Qiskit library, which are the multiply controlled NOT gates, and then find the best number of iterations for each of the instances that we tested. We're going to understand better how these steps are solved once we will understand in the next 3 slides how our solver, which is based on Nannicini, so in the same 3 steps, is going to be generalized. In order to understand it better, we are going to stay with problem 4 until the end of the discussion. It is an exactly-1 for SAT over 4 variables and clauses. So we have n, m, and k that are equal to 4. In particular, here in the bottom, you can see the definition of the clauses. And we're interested to, in particular to C1, since we're going to use it in order to describe the second step of the algorithm. And it is x1 with positive polarity, x2, x3, and x4 that are instead negated. Okay, so we can start to talk about the first step of the algorithm, which is the initialization. In particular, as we said with Groover, we have to bring all the basis states to the uniform superposition. To do so, we easily apply Hadamard gates on all the n qubits storing the variables of our problem. And so we can start to understand here the first issue that we mentioned before related to the number of qubits needed in order to precisely define the circuit for each of the instances. Since in Nannicini, he at most solved 3 SAT over 3 variables and 3 clauses. And so he well knew a priori which was the correct number of qubits to solve his problems. In our case, we're dealing with several instances that we do not know a priori. And so we had to find a way to scale our circuits in order not to waste any qubit possible. Understanding from the initialization is that we will need n qubits for each of the variables plus an additional one, which is the output register of the function that we are encoding. That, as we can see, it is first negated because this qubit will have a probability with a certain probability, the value of 1, if only if the solution of our problem actually exists. Now, we can start with the second step of the algorithm, which is the most complex one, since we want to encode the entire matrix UF inside the circuit. In fact, to do so, we decomposed the problem in multiple steps. Well, m multiple steps, which do the same thing for each of the clauses. As we can see, we want to encode a circuit like the one in the figure that brings on an additional ancillary qubit the possibility of having an exactly one true literal for that particular clause that we are encoding. In the end, so for each of the m clauses, we will bring the final result of the conjunction of all the additional ancillary qubits to the final only output that we defined at the beginning. As we can see from C1, we first bring all the 4 variables of the problem with their respective polarity to the correct corresponding qubit. And in the end, we apply a multiply control NOT gate between all the variables defined in the clause. This means that if we have 4 clauses in the variable, we will have a quadruply control NOT gate here, but still in a 4SAT problem, we can have 3 or 2 clauses or even 1. And so here we will just need to realize that multiply control NOT gate targeting still Q10 or the corresponding qubit of the clause. As I was saying, in Qiskit, we are allowed only to realize doubly control NOT gates. And so we had to deal with this issue by adding the least number of qubits possible. This is the solution that we have in the real circuit of the execution of problem 4, in particular the one between the 2 barriers and the purple in the purple lines. As we can see, we conjunct the result of doubly controlled NOT gates using additional ancillary qubits, and in the end bring the final result to Q10. So now we understand that we have n+1 qubits for the initialization, m ancillary qubits for all the variables, since following C1 we will have C2, C3, and C4, and in the end these 2 additional ancillary qubits. It would be very dispendious to add 2 qubits for each of the following clauses that need the multiply control NOT gate to be realized. And so we managed to reset the state. And to do so, it is as simple as applying once again the same gates, targeting them so that we can reuse these qubits for the following clauses. So now we can understand which is the complete number of qubits that we need in order to realize our particular quantum circuit for each of the instances that we're testing. So we have n+1 for the initialization, m for each of the clauses, no, m in total for all the clauses, and then n-2 because we can use at most doubly control NOT gates for the generalization of the multiply control gates. Hence, in the end, we have 2n plus m-1 qubits that in this case we can count are 2 times 4, 8, plus 4, 12, minus 1, 11. And as we can count here, these are in fact 11 qubits. So once we have encoded all our clauses, we finally reach the last step of the algorithm, which is the inversion about the average. In particular, it is defined over a unitary matrix called W that still needs the generalization of the multiply control NOT gate. In this case, to realize the diagonal matrix D over which it is defined. As we can see in this circuit, we exploited the same trick that we used in the problem encoding step and realized the triply control NOT gate required. Okay, so from this last slide, it's very important to understand that the number of iterations that we were mentioning at the beginning of the presentation. So the problem encoding and the inversion about the average steps are the ones that are iteratively repeated in order to increase the coefficients, the ones that we do not know a priori how many times to iterate. As we can see here, the inversion about the average is followed by the measurement. So we understand that this is the last inversion about the average of our iterations. And so we're able to measure the quantum state by making it collapse to a classical register of 4 qubits, of 4 bits, now we are in a classical world, that will be displayed in the histogram in order to see the probabilities of having the correct solutions. Okay, so now that we have understood how the generalization works, we can start talking about the results. But first of all, it is important to mention some preliminary considerations. The first one is related to the fact that we consider 4 problems to describe our results. The first one is needed in order to prove the consistency with the solution obtained by Nannicini in his solver. The second is used in order to display how we are not able to choose a solution once a histogram has a particular shape. And the third and the fourth one are the actual generalization. In the third problem, we generalize in terms of clauses and variables, so m and n. And in the fourth one, in terms of the maximal length k that of the clauses. Well, the most important consideration to be done is the fact that all the algorithms, all the times that we run our algorithm on the different instances, we used the simulator provided by the Qiskit library, since we also tested the execution on the real quantum machines, but they're not possible because we obtain a too long circuit whose execution time is longer than the circuit repetition rate. However, we will discuss in the conclusion, also related to how Qiskit library works, why we expect that our results will be still consistent once the execution of on the real quantum device will be available. In order to present the result, we will see 2 figures for each of the problems. The first one on the left is the ones that is obtained once we run the algorithm with the best number of iterations. And the following is the one that is returned once we try to enhance it by doing an additional iteration. But as we said, still from the quotation from Kirsten-Fuchs, is like having an overcooked souffle, and so the probability distribution spreads all over the other incorrect combination and decreases for the correct solution. Okay, so as we said, in problem 1, we just want to prove the consistency of our solver. In particular, we obtain the correct solution with 2 iterations. It is the same one of Nannicini, and the probability is around 95% as he obtained. We can start to grasp from this problem what happens if we add an additional iteration. As we can see, in fact, the probability spreads all over the other incorrect solution and decreased of around the 60% for the correct one. Now let's consider problem 2. It is the one with no solution. However, it seems trivial that a solution for the general SAT problem actually exists. For example, consider x1, x2, and x3, which is a solution for the general SAT, but not for the Exactly-1 formulation. In fact, it is correct that for C2, x2 is the only true variable that makes the clause true. But for both C1 and C3, we see that 2 variables are now present for C1, making it true, and for C3, all the variables are making the conjunctive normal form true. As we can understand also from the histogram, we see that all the combinations have almost the same probability, and this is the reason why we're not able to distinguish one combination among the other to return the solution. Now we can start with the more interesting problems. The problem 3 is the one that generalizes in terms of variables and clauses. In particular, we still have a 3 SAT, but with 5 variables and 5 clauses. We see from the solution with 3 iterations, so the best one, that the correct solution is provided with a probability around the 40%. It is very detached from all the other incorrect combinations that reach at most the 7.9%. And if we try to run the algorithm 1 iteration more, we see the relation with what we said in the quotation. In fact, the probability spreads all over the combinations, in particular, raising to almost the 16% for a random one, which is 00101, now very near the 27% of the correct solution that is decreased of around the 10% from the previous case. The last problem, our famous problem 4, is a 4 SAT over 4 variables and 4 clauses. So now we're generalizing in terms of also the maximal length. It is the one that provides the best results with 3 iterations and with a correct solution that rounds the 96%, very completely detached from all the other incorrect combinations that at most reach the 0.6%. And as always, if we tried to run an additional iteration, we see that the probability shape is almost the same. However, it decreases of around the 50% for the correct 40% for the correct solution, and spreads almost to the 3.5% for all the other incorrect combinations. And now that we have explained also the results of our solver, we're able to draw some conclusions of our work. The first one is that all the instances that we tested are consistent with the solution that should be provided. In particular, we also focused on several other problems, and always the correct result is returned by the solver. The most important feature to consider is that all the solutions are provided with a very high probability with respect to all the other incorrect combination. And this has to be kept in mind for one of the following conclusions, that since it is going to explain why we expect that the execution on the real quantum devices will still be consistent. Generalization limits wants to explain a bit the title of our work. In particular, it says generalization for arbitrary number of variables, clauses, and k, but actually how big is this arbitrary? Well, in order to understand it, I made a sort of definition for the Exactly-1 formulations that I studied, and we consider as dense a problem that for each of the clauses has a number of variables that reaches the k, while in the other case we have a sparse problem. With this definition, we were able to see that already with a 5 SAT over 5 variables and 5 clauses in a dense formulation, the problem, the solver is not able to find the correct solution due to the decoherence problem that rises, making it impossible to distinguish one solution among the others, while for a sparse formulation of a 7 SAT over 7 variables and 7 clauses, we're still able to find the correct solution. Talking about technology, as we were saying at the beginning of our results, we run all these instances on the simulator provided by the Qiskit library. And because the execution of the most powerful quantum machine provided by the IBM Quantum Experience, called IBM 16 Melbourne, is still not too powerful to run these instances. In fact, we obtain 2 long circuit, as we said before, with an execution time that is longer than the circuit's repetition rate. However, the feature of having a very high probability leads us to expect that once in the real simulation, noise will be introduced also for all the other incorrect combinations, the gap between the correct solution and all the other will still be present, and so we will still be able to distinguish the correct solution among all the others. As I said almost during all the presentation, and also as you can find at the repository that is linked to the paper, the one that I used in order to make my whole study on the quantum computing world, everything that we did is made on Qiskit, one of the most spread and known libraries in the quantum community. In my opinion, it is also very useful to start understanding the quantum computing world. As I said before, I started almost 1 year ago and became a contributor to the library almost 3 months later. Obviously, not solving a particular physics problem, but an issue that was mostly related to software engineering. However, this allowed me to become a contributor and start studying more complex and also physical issues. The last conclusion is related to the number of cycles that we have also kept together during all the talk. And this last slide talks about a possible future work related to them. We deduced from the execution of all these complex instances that there is a sort of relation between the number of cycles and the complexity of a problem. In fact, having more complex instances leads to have a more possible combination for the correct solution. And so this is consistent with what the steps that are iterated do. Hence, they are draining more the probability from the incorrect solution and putting it to the correct combination instead. As we can see from this last table, we have recapped the problems that we studied with their complexity and M and K, and the best and the next solution that we were able to find. In this case, we need to test for each of the problems one at a time the number of iterations in order to find the histogram with the highest probability. While this possible future work should be the one of finding a formula that concatenates, that allows to find the cycles once we provide the complexity of a problem. And talking about this, it should be also interesting to understand how to define the fact that a problem is dense or sparse, because we saw that affects a lot the execution of our algorithm. Okay, so this was all for my presentation. Thank you very much for attending. And if you have any question, please feel free to do it. Otherwise, if we have time, I do not know how many time it took this presentation. I have also a brief demo in order to show how the actual run of problem 4 works.
Actually, you have a couple of minutes, Francesco, if you want to show us this demonstration.
Okay, okay. So I've already, tell me if you can see it. Now, can you see the code and
We can.
Okay, so, okay, this on the right is just the main class of the solver. It is obviously realized in Python since we're using Qiskit, but what we're interested in is the file on the left, as also it is described in the paper. This is the formal definition of problem 4 in the notation that we used. As we can see on each of the lines, we have a different clause. In the first line, so we have clause C1 that we found in the problem encoding step. In fact, is x1, x2 negated, x3 negated, and x4 negated, and the followings are all the others. So in order to run the algorithm, we use Python, calling the main class and passing 3 parameters. So the first one is the file containing the formulation of the problem. The second one is a Boolean variable that is used in order to decide whether to run it on the simulator or on the real quantum machine. In this case, as we mentioned during the presentation, we run it on the simulator. And the final parameter is the number of times that we want to iterate the 2 steps. In this case, we say 2, since we know that for problem 3, from problem 4, 3 are the best number of iteration, but Qiskit is not able to display such big circuits and renders it not correctly. So in order to understand better the final circuit, it is easier to see it with the 2 iteration. So now once the execution has finished, we will see the results in terms of the histogram. That is going to be mostly the same that we talked about in the discussion. However, the probability is a bit slower because 2 is not the best number of iteration for problem 4, but the most important thing that I wanted to show you is this final circuit. First of all, can you confirm that you're watching a very big circuit? Yes. Okay, because I don't see your faces. Okay. Yes.
Yes, we can see.
I think you are. Okay, so this is the final circuit with just 2 iterations to find the solution. If we zoom a bit in, we can see all the steps that we mentioned during the presentation. So this is the initialization. Here we can recognize the encoding of clause C1 and then the following clauses. As I was saying, the multiply control NOT gate will be realized just on the variables that define the clause. In this case, we have just x1 negated, x2 and x4 negated, and so it will bring x1 and x2 to the additional ancillary qubit, and the final result is going to be stored on the corresponding qubit of the clause. So here we did 2 iterations. In the end, after we encode all the clauses, we can see the first inversion about the average, and then another cycle starts. So we first encode once again clause C1. Here it should have been better to add an additional barrier. These are the NOT gates of the variables x2 and x3. Then we have already once more clause C2, clause C3 is here. And in the end, we can see the same figure that we presented in the discussion, the last inversion about the average and the measurement, which brings the quantum state to the classical register, where it collapses to a string of 4 bits that allow to find and distinguish the solutions. So this was just to present how the circuit will be finally, also to grasp why it is still not possible to be run on the real quantum meshing, because the Qiskit library makes, with the transpilation function, a sort of optimization and tries to reduce the number of qubits adding additional gates. But the number of gates added from a circuit that is already so long is that many that we obtain a circuit that is that long, whose execution time is longer than the circuit's repetition rate. And so this is the error reported by the IBM quantum experience, and what makes it impossible to test it also on the real simulator. Okay, I finished.
Okay, thank you, Francesco. Actually, your work was awesome, in my opinion. This is quite promising. So, thank you. I don't know if someone have a question. I have one, but let start the audience if they have one. Some questions? Okay, so in that case, I can ask. I'm worried about the scalability of this method. You can see here
Yes.
the outgoing circuit is not really small.
Yes.
So actually, you mentioned some problem with when you try to execute it with IBM Q experience. So I understand that, of course, technology is a limitation, but apart from technology, what's your opinion about scalability issues you can find with this solution?
Okay. Well, first of all, in my opinion, it is important to understand what the SAT problems are used for, because here, as I also said at the end in the conclusions, the most complex instance that we were able to test is the 7 SAT with 7 variables and so close it. But in applications, if I'm not wrong, I read a lot of, in particular for artificial intelligence, that problems of the Exactly-1 are mainly studied for a maximal length of 4. And in fact, as Nannicini stopped with his work, he studied with 3 maximal lengths. So the scalability of this work, in my opinion, it is important, in particular because since we're not still able to test it, a solution should also be the one of running the iteration a less number of times, so obtaining a slower circuit. Because as we can see from this picture, this is a solution obtained with 2 iterations. But as I said, the best iteration is obtained with the best solution is obtained with 3. And in that case, we had once more the problem encoding and the inversion about the average step. And we saw that I think that the solution is still present. We obtain with 2 iterations a 91% of the correct probability, while in the with 3 iterations, as we can see in the presentation, the solution of the 4SAT is around 96%. So it just changes the 5%, which it should be a lot or not, depending on how much noise is introduced inside the real instead the real result returned by the quantum circuit. So this is a bit my opinion related to the scalability.
Okay, thank you, Francesco.
You're welcome.
Good. Thank you again for your interesting talk.